subscribe to our channel for latest video series on GATE, UGC, NET and more. Also press the bell icon so that you never miss an update on any latest video. For more information you can visit our website or call on the numbers below. Okay, so hello people, we already looked at some basic signals, unit impulse, step and ramp, and we've discussed that all these signals can be expressed as differentials and integrals of each other. So in today's lecture we are going to look at how we can express them as differential or integrals of each other, and also how to solve some questions related to them. So we are starting with unit step. See, how are we able to express unit step as differential of unit ramp or integral of unit impulse? We are representing unit step as, right, this is the definition of unit step that we are using. Now see, whenever you are having any function, any y of the form mx plus c, this is the definition of a line. This is how you are representing any line in yx plane, xy plane, okay. So when you are differentiating this y, when I am differentiating this y with respect to x, differentiation of this mx is going to be m and differentiation of this constant is 0. So when I am differentiating a line, what I obtain is its slope, okay. That is why we say that differentiation of a line gives it slope. Now look at the definition of ramp function, RT. We defined ramp function like this, right? This is what we gave the basic definition of a ramp function as. Now see, when you are just differentiating this function, when I differentiate this ramp function, what do I obtain? See, this RT was defined as t for all values of t greater than or equal to 0. When you are differentiating t, you are going to obtain 1 for all values of t greater than or equal to 0, and it was already 0 for values of t less than 0, so this is going to remain as it is. See, this definition matches exactly with the definition of ut. That is why we are saying that this ut function is differentiation of ramp function. Unit step function can be obtained by differentiating a ramp function. Now suppose we are having a ramp function which has slope other than 1, okay, which is having some different slope, some other slope. Then what are we going to obtain? We are going to obtain a step of different size. That is, we are not going to obtain a step of one step of unit, we are going to obtain a step of different size. Only the step size is going to change according to the slope of ramp function. Also, if this ramp function is shifted, then the instance of slope change is going to tell you the instance of step change. Okay, that is how it's working. Now see, this is how we are defining unit step. If I just differentiate this signal, differentiate means, see, this function is only a step change, only a discontinuity, right? This is only a discontinuity at t is equal to 0, nothing else. It does not signify anything else. So to represent a discontinuity, when I am differentiating this signal, I am going to obtain unit impulse. See, impulse is just representing a instance of time. It is only representing a change in time, only it occurs only at t is equal to 0 and having value infinite. Infinite value means, signifies that this function, see, this function jumped from value 0 to 1. So when I am differentiating this signal, when I try to find what am I going to obtain? I am going to obtain unit impulse function, where change in step is going to define area of the impulse, okay, size of the impulse. See, impulse is having value infinite, okay, so we cannot comment about the value of impulse, although we can just comment about the area under the impulse function. Generally we consider the area under the impulse function as 1. That is why, see, we've already talked about this, I guess. Impulse is existing only at a single point of time, so you cannot talk about its area, because for defining area of a signal, it must exist between two unique boundaries of time. This impulse function exists at a single point of time, so we cannot define its area very clearly. So we are just considering the area of this impulse function as 1. We have talked about this, I guess, that we consider that it is existing between two boundaries, where the two boundaries are considered to limit to 0, okay, approaching 0. Fine. So we considering that this differentiation of this unit step is going to be impulse. So whenever you are required or You want to find derivative of a function, derivative of a graph. What are you going to do? Suppose the graph consists of straight lines. When you are going to differentiate that graph, what you are going to obtain? You are going to obtain steps. And if this graph consists of steps, when you are going to differentiate it, you are going to obtain impulses. Okay, so we are going to look at an example now. So, we are given a function, we are given a graph which looks like this, and you are required to find the integral of this graph. So, I am going to do it both graphically as well as by representing the function. So, if I just try to represent this function using impulse signals, what I can write? See, the value of these impulses, value of these numbers are representing area under the impulse, and this area under the impulse is going to be the coefficient of the impulse function when I am going to write it as a function in the form of a function. So, suppose I consider it as ft. So, I can write ft as, this is the impulse of area 3, so this is going to be written as 3 into del. This is occurring at t is equal to minus 1, so I am going to write it as del of t plus 1. This is the impulse of area minus 5 del t minus 2, and then I am having an impulse of area 9 del t minus 6. Now see, if I just try to integrate this, okay, I am going to integrate this, what is going to happen? This is going to become, suppose I am considering it as something gt. This is going to remain same, this is a constant anyways, right? So this is going to remain same. Integration of del t is going to be ut, step function, and the point of existence of the step is, impulse is going to become the point of existence of step. So this is going to be a step at minus 1, okay. Similarly, this is what the integration of this function is going to look like. If I just try to sketch this function, what happens? So at t is equal to minus 1, I am having a step of plus 3. So before t is equal to minus 1, I am going to have value 0. At t is equal to minus 1, step of plus 3, okay, which is going to continue till t is equal to 2. Right, so this step is going to continue till t is equal to 2. At t is equal to 2, we are having a step of minus 5. We are having a step of minus 5 means the final value of this function is going to be minus 2. Already we were having a step of 3. Now we introduced a step of minus 5, which makes the final value of this function as minus 2. Minus 2. Right. Now again I have a step of plus 9 at t is equal to 6. This is going to make the final value of the function as 7. Right. So this is how integration of this function is going to look like, okay. This is gt. Fine. So this is how we are finding integration of functions. Now if I ask you to find integration of this function, okay, this is also a function, right? This is step function. Now I suppose it is required to find integration of this function. So we know that any function which is consisting of steps, if you're going to integrate that, you're going to obtain a function of ramp type. Okay, let's just perform integration of this function also. Okay, suppose we are calling it as yt. What we are going to get? This 3 is going to remain same. Integrating ut, we are going to obtain rt. Right, so this is going to be the integration of this function. If I just try to sketch it, what is going to happen? We are having a step of size 3. Step of size 3 means slope of the line, okay. Slope of the line which occurs at t is equal to minus 1 is going to be 3. So we are starting at minus 1. We are having a slope of line 3 which is going to continue till t is equal to 2. So we have discussed this. We can find the final value of this line, right. Slope is change in y upon change in x. We have seen this, okay. So change in x is going to be 3. So accordingly change in y is going to be 9 for the slope to be 3. So this is going to be a line which has final value as 9. This is going to be 9, okay. At t is equal to 2, we are having a change in slope which is of -5. So the final slope of this line is going to be -2. Now the initial value of this line was 9. Now we need a slope of -2. So we are just calculating final value, okay. And the next slope change occurs at 6. So change in x is going to be 4. So final value at t is equal to 6 is going to be -1. Okay. Right. Now at t is equal to 6, we are having a slope change of 9. So the final slope of the line is going to be 9, okay, and it's going to continue like that only. Fine, so slope of this line was 3, slope of this line was -2, and slope of the line that follows forward, slope of this line is going to be 9. Okay, so this is how integral of this function is going to look like. Similarly, if we just differentiate these functions, see, from -1 to 2 there was a line of slope, okay, sorry, line of the slope is going to be 7, okay, 9 is the change in slope, okay, 9 is the change in slope. Already we were having a line of slope -2, so finally the slope of the line is going to be 7. So if you just look from here, -1 to 2 there was a line of slope 3. When I differentiated it from -1 to 2, I am having the value of the slope only, value of the slope was 3. From 2 to 6, the value of the slope was -2. So when I am going to differentiate this function 2 to 6, I am going to obtain the value of the slope which is -2, and from 6 onwards I am going to have the slope as 7. So this is how the differentiation of this function looked like, okay. If you just differentiate this function also, you are going to obtain the original function, okay. See, what did that function represent? Only the points where the discontinuity is lying. We are having discontinuities at -1, 2 and 6. So the differentiation of this function is going to contain of 3 impulses. Of what size? Of whatever size the discontinuity is. This is a discontinuity of size 3, so I am going to have an impulse of size 3. This is a discontinuity of size -5. Why -5? Because originally value was 3, finally was -2. So discontinuity of -5 and discontinuity of 9. So differentiation of this function is going to have 3 impulses of sizes 3, -5 and 9. Okay, so this is how we are expressing signals as differentiation or integrations of each other. Now the same procedure we are following in discrete time signals also, okay. We can express them as difference or summation of each other. We are going to look at it now.